This is the video on Newton's first law. So remember, in these videos, there are two codes. One will be a written code that will come up on the screen, and one will be a verbal code said by myself. Each code will be 3 numbers, and you will need to have these codes in order to move on with any homework assignments. So remember, when you're looking at these slides or watching this video, what's really important is green. You can make a nice little notebook out of the green text. So look what's that in green. So this is the written code. I would recommend writing this down somewhere. All right. So the big question for Newton's first law is, what is inertia? So inertia is a property of all material bodies to resist a change in their motion. Now, inertia is just a made-up word. You can still measure the amount of inertia a body possesses by measuring its resistance to acceleration under an applied force. Now, we define mass as a measure of the amount of inertia a body possesses. So we've learned about mass. We said it was just the amount of stuff that an object has, but more scientifically, it's just a measure of the amount of inertia, or the resistance to change in motion. So you've probably all heard Newton's first law: object at rest will remain at rest, object in motion will continue in motion unless acted upon by unbalanced force. Well, Newton's first law of motion is also known as the law of inertia. It basically just states what inertia is. Objects at rest remain at rest. Objects in motion remain in motion in a straight line unless acted upon by an unbalanced force. So let me just propose a new way to look at Newton's first law, one that is a little more mathematical, right? So if you can see that there, remember the symbol used to represent net force is that we got net force. You hopefully remember net forces produce change in motion or acceleration. Another way to write Newton's first law of motion is this equation. So net force implies acceleration, basically, right? If a net force is applied to a body, that body will accelerate. If a body accelerates, then there must be a net force applied to it. You cannot have one without the other. In other words, net force implies acceleration. Acceleration implies net force. Both the state of rest and constant velocity are natural. Acceleration is the only real motion. It requires no force to keep something moving at a constant speed in a straight line. If an object changes its motion, speeds up, slows down, or changes direction, then an unbalanced force must have been applied to it. So I said this would show up. Again, remember balanced versus unbalanced forces. Balanced forces, all forces cancel out. Net force is 0 newtons, and the object is at rest or at a constant velocity in a straight line. Unbalanced forces, all the forces do not cancel out. Net force is not 0 newtons, and the object will be accelerating. So I like to think of it as astronauts out in space. Well, whether you're at rest or a constant velocity, your net force is 0 newtons. But if you happen to get into a spaceship with an applied force, a net force, then that object will be accelerating. So in order to demonstrate this, we did the Shake It Lab, where you shook a full bottle and an empty bottle of sand. And what I wanted you to get out of this one is that when you're shaking it, what you're feeling is the inertia, right? You probably say, well, it's obviously harder to shake the one filled with sand more than the empty one. Well, and you'd say, well, because it's heavier. Well, it is heavier, but that's not why it's harder. Because if you were to go to the International Space Station, where we remove gravity from the situation, that full one would still be just as difficult to shake back and forth. And it's because you're feeling that bottle's inertia, right? You're feeling the inertia. If you were to hold them straight out, hold them up, then yes, you'd be feeling the weight of the bottle. Just another way to reiterate this: what's the best strategy for escape when being chased by an alligator? An alligator can run faster than you, 20 miles per hour, right? But an alligator has more of a mass, 225 kilograms. Average human has a mass of 62 kilograms. So the alligator has a larger mass, meaning it has more inertia. So the alligator may be faster, but you would be able to turn quicker. It would take more of an effort for that alligator to change direction or to change its motion than you would, right? You would be able to turn quicker, run away in a zigzag motion, and you should be able to get away with nothing but an interesting story, right? So this works with most things larger than you, but there are obviously some creatures where you're supposed to stay still or walk away slowly. But as a last-ditch effort, if you're being chased by something much larger than you, best bet, zigzag, right? If it's an absolute last-ditch effort, zigzag. Alligators are more ambush predators, though. Usually, if you survive that first strike, you're good, right? Now, this brought us to an inertia simulation. And what I wanted you to get out of this one is what happens to that water level in that cup. So that person is applying a force to the cup, not the water. That's why the water appears to be tilted in some of those situations. And that answers this question: why is it hard to drink in an accelerating car? So if you're a passenger in a car in arrest, the driver slams on the gas pedal, it feels like you go back and you're being pushed back. Nothing's pushing you back in the seat, though, right? If you're a passenger in a car going 30 miles per hour, the driver slams on the brake, well, it feels like you're going forward, right? But nothing's pushing you forward. You're a passenger in a car going 30 miles per hour, then they turn to the right abruptly. Well, it feels like you're being pushed to the left, but you're not, right? So in all of these scenarios, the car is accelerating around you. You have inertia and are resisting that motion. If you're holding a cup of water, the same thing happens. Everything around that water is accelerating, and that water has inertia, which means it resists that change in motion. Essentially, someone slams on the gas pedal, the car accelerates, you don't. You are going to continue doing what you're doing, and eventually that car seat is going to push you forward. That's why it's really hard to drink water in an accelerating car, because everything accelerates around you and you would accelerate into the water, right? How much confidence do you have in the laws of physics? So this one is like, if you've ever, you've probably seen videos of this one about somebody spinning a cup around and the water staying in there, right? So the water has the tendency to continue in a straight line. You can see that blue line. The water is resisting that change in motion. The water is traveling in a straight line. The cup is providing an inward force, keeping the water in the cup. So it's the same thing think about a car turning, continuously turning, and it feels like you're being pushed to the outside. You're not being pushed to the outside. What happens is you have inertia. You have the tendency to continue in a straight line, and that car is providing that force that's pushing you inward. If you do it fast enough, you can keep water in a cup as it spins around. How does the tablecloth trick work? So at this time, I'll go ahead and give you the verbal code. The verbal code is 824. I say that again, the verbal code is 824. So the tablecloth trick, you can see you pull a tablecloth and the tablecloth comes out, but think about what you're applying a force to. The person is applying a force to the tablecloth. The dishes on the tablecloth have inertia and are at rest. They have the tendency to stay at rest. As the tablecloth is sliding, there is a small kinetic friction force, but it happens so quickly, it's not enough to pull the dishes off the table. So we did this lab. It's called card, coin, cup. You can do this one at home real easy. You just basically place a playing card on top of a cup, place a coin on top of that card, and you just flick the card with your finger, and the card should slide out, and the cup or the coin should fall into the cup. Now, it's because you are applying a force to the card, not the coin. The coin has inertia, and it's at rest. It has the tendency to stay at rest. That card goes out from underneath it. That coin stays at rest and will eventually fall into the cup after the card has left. So once again, there is too much unknown in the universe to take a break from learning. Get out there and question everything.